Good day, everyone. My name is Ali Mahmood, and we will be presenting our issued paper titled Design, Fabrication, and Performance Evaluation of a Hybrid Linear Generator Reciprocating Air Compressor using a magnetic coupled piston, or in a short way, as we like to call it, a hybrid compressor. Our presentation will begin with a restatement of our thesis, which kinds of go over the importance of industrial use. We will give a brief background information of how industries could benefit from hybrid compressor. Following that, we will discuss the design, fabrication stage, and end with the interpretation of the results. In our issued paper, we argued that on a yearly basis, worldwide, industries consume nearly half of the total power generated. This number keeps on rising due to the global economic growth. It is said that motors are considered to be the heartbeat of the industry. These motors are highly responsible for such titanic consumptions. They are used to run conveyors, refrigeration, air conditioning system, and other automotive systems. Half of the total energy demand for the industries is used primarily for air compression. With such consumption, there is a dire need of sustainable design to lower the carbon footprint and for energy efficient air compression system. The idea is to design a reciprocating air compressor whose piston is the translator of the linear generator. Under operation, the compressor functions as a conventional reciprocating air compressor but generates electrical power at the same time without significantly compromising its compressive work. Thus, the overall efficiency of the compressor is expected to significantly increase because of the extra electrical power output. So this process flow diagram showcasing the step-by-step process of how we design the system, followed by fabricating it and performing test evaluations to gather the data and analyze it. The first part would be the design of our piston, where we initially use a block of high steel material as the piston head. We reformed it using a lathe machine. However, during the operation, we found out that the lathe machine was not able to handle the toughness of high steel. So as a result, the cutting tool broke down and the block of steel was replaced with aluminum. Our team performed the same operation as we did in the steel block, like using the lathe machine for facing the end part of the piston head, cutting it to be in specific dimension, boring it to attach the piston rod, straight turning for adjusting the diameter, grooving the placement of neodymium magnets, and finally chamfering for the purpose of attaching the piston rod. The important aspect about the design of the piston is that in the grooved area, we use super glue to attach the neodymium magnets because our piston will act kind of like a linear generator. Why did we attach it? Because following Faraday's law, when you equip magnets to a piston and it moves in a cylinder covered with magnetic coils, voltage would be generated. And this voltage is the result of the change in the magnetic field of the coil. Next, in the design of the connecting rod, we use a bar of metal. And we reformed it by changing the shape using a milling machine and a drill press. Two of its ends were drilled with a drill press to attach ball bearings to help reduce friction. The unique part of the design of our connecting rod is how we structure the thickness of the middle part. In here, our team used a milling machine to reduce the thickness so that the connecting rod does not hit the inside surface of the cylinder and to give allowance during the compressive work. For our flywheel, we salvaged it and we continued to weld it. After welding, it has been furnished and repainted for aesthetic purposes. Holes were drilled to connect it to the shaft of the motor. For our cylinder, the cylinder was made from acrylic plastic, which was ordered and specifically manufactured from the manufacturing company. Due to the manufacturer standards, it was not available in our specific dimensions. Adjustments were made where the cylinder underwent straight turning operation for the placement of coils and steel rings. For our galvanized iron steel, a plasma cutter was used to cut the GI sheet into our designated rings. We use large and small rings ranging in different sizes of outside and inside diameter. For our magnetism and electromagnetic induction, the linear generator was designed with 9 slots. Two sets of toroidal rings were made using a winding machine. It was made with American wire gauge with 500 turns in total. The leftover wires are being used for the next rings by connecting the 2 wires with soldering to save the cost of the expense. In order to measure the efficiency of the air compressor, linear generator, hybrid linear generator reciprocating air compressor, and to establish the load characteristic curve of the hybrid, 4 cases of study were conducted. There are varying air compressor speed, hybrid generator at constant speed, linear generator at constant speed, and hybrid generator at 100% load and varying speed. The first test was conducted in a room with ambient temperature of 21 degrees and intake pressure taken as 1 atmospheric pressure. This test was designed to measure the efficiency of the air compressor when the linear generator has no load. The speed of the motor is varied to determine the work of compression. 5 trials were performed decreasing the speed of the compressor from 340 to 140 revolutions per minute. As you can see from the 2 figures, the speed of the compressor varies the work of compression. At a speed of 300 to 350 revolutions per minute, we recorded a maximum efficiency of 24%. The loss in speed significantly affected the efficiency of the air compressor. It was designed to run at 500 revolutions per minute. However, due to misalignment in the connecting rod, we could not run at such speed due to excessive vibration. For our second case, we tested the linear generator at constant speed, and varying intake and exit valves of the compressor were left fully opened so that to ensure that the compressor is not doing compressive work. At a constant speed of 360 revolutions per minute, 7 light bulbs with maximum power of 29 watts were used as loads. To establish the load curve of the linear generator, the load was varied from no load to full load, incrementing 25% at each trial. At a constant speed of 360 revolutions per minute under no load condition, the output power and efficiency was 0. At 25%, we found it to be not cost effective. At 50%, it starts to reach its maximum point. It starts to show some potential. So at 75%, the input power is the lowest in all the trials, which is a good thing. And the generator has reached its maximum peak point. And it has an efficiency of 3 times that of the 50% trial. However, the 100% load would cause an increase in input power with small increase in efficiency. Therefore, it is best to run the linear generator at 75% load. For case 3, the compressor and linear generator speed was kept constant while the load was varied from no load to full load. This was performed to provide a basis of comparison between the first 2 cases. As the load increases from no load to full load, the output power of the linear generator also increased. The lowest efficiency was at no load condition. Hence, it is not recommended to run the system at no load, since the motor will draw the highest current and heat up. From 25% load to 75% load, the input power decreased, while the combined output of the hybrid system significantly increased. So for the last case, in order to establish the relationship of the hybrid system under varying speed and 100% load, 7 light bulbs were connected to the system as a fixed load and the speed was varied. Based on the output curve, we obtained an overall efficiency of 9%. At higher speed of 320 revolutions per minute with a combined output power of 207 watts, we generated an efficiency of 22%. At this speed, the motor draws in much power as seen in the curve. So in conclusion, this shows a full load testing operation of the hybrid compressor running at full load. The primary aim of this research paper was to evaluate the concept of cogeneration through the hybridization of a reciprocating compressor and a tabular linear generator, which has not been performed thus far. 4 tests were performed using 4 different test conditions. It was found that the work of compression varies with the speed of compressor. An increase in speed increases the work of compression as well as the input power. The maximum recorded efficiency was recorded at 24%. Varying the load of the linear generator affected its performance. The optimum load was at 75%. At this load, the efficiency was 3 times that of the 50% condition. At full load and motor speed of 320 revolutions per minute, both the motor draws in more power with an efficiency of just 22%. In our recommendation part, the main input power source of the prototype was selected to be an electric motor, which was not manufactured to be controlled with varying rotational speed. Without reaching its designated rotational speed, one of the capacitor with lesser capacity would be heated up and produce smoke. Its designated rotational speed is 1,730 RPM, but our prototype was not able to handle that high speed. Also, due to the incapability of varying speed by itself, a commercial speed converter was used. This allowed changes in rotational speed, but it was not able to produce stable rotational speed. Lastly, despite using one of the strongest magnets, we were unable to find a ring-shaped magnet with application size to the piston. Instead, small circular magnets with diameter of 9 mm were used. There was an air gap in between every magnet, which was not conductive for maximizing magnetic flux. And that's all. Thank you for listening. Thank you.